Alright, so today we're going to be looking at a situation involving a coaxial. So basically what that is two concentric cylinders with a fluid in between. The inner cylinder is spinning and the outer cylinder remains constant. And so if we look at this from the top view, it looks something like this. And we're going to have the inner radius, we're going to have an outer radius. So the inner radius is the radius of the inner cylinder, the outer radius is the radius of the outer cylinder, and then we're going to use the variable r to denote any distance between those two radii. So we've been given the velocity profile for the fluid that's between the two cylinders, and that is given up here. It depends on the angular frequency, this constant k, which is a ratio between the two radii, and r, which is our position between the cylinders. So we can do a quick check and show that this does match up with our situation where the inner cylinder is spinning, has a velocity, and the outer cylinder does not have a velocity. So we'll start by looking at the inner cylinder, which has a radius ri. So we've got the velocity is equal to the angular frequency, and then I'm going to plug in the ratio for k. So we got inner radius squared over the outer radius squared over 1 minus the inner radius squared over the outer radius squared, and then that times the outer radius squared over the inner radius minus the inner radius. Right, and so we can find a common denominator for these two. So we've got the velocity is equal to omega. We'll keep the numerator the same. And then on the denominator we got outer radius squared minus the inner radius squared over the outer radius squared. And then this is going to be times outer radius squared minus the inner radius squared over the inner radius. Alright, and so then we can see that we've got some things that cancel. We've got this that cancels. One of these cancels with one of those, and those cancel. So in the end, we've got the velocity is equal to the angular frequency times the inner radius. So that shows that yes, the inner cylinder is moving. So we can do the same thing with the outer cylinder, which has a radius of big R. So that would be velocity equal to omega. And I'm just going to leave them for case this time. And then we replace all of the r's with the outer radius. And we can see that this term goes to 0. And so the entire velocity is multiplied by 0. So the velocity is 0. So from that, we can see that yes, the inner cylinder is moving and the outer cylinder is staying still. So the next thing we're going to look at is the shear rate that we were given. So this is just general shear rate in cylindrical coordinates, and we need to adapt to this situation by plugging in our velocity profile. So first thing we need to do is divide the velocity profile by r. So velocity profile over r is equal to omega times k squared over 1 minus k squared, and then times the outer radius over r squared, so this is where we're dividing that r, minus r over r, which is 1. Next thing we want to do is we're going to take the derivative with respect to r. So derivative with respect to r of velocity profile over r is equal to omega times k squared, 1 minus k squared, times negative 2 r squared over r. Negative 2 outer radius squared over r cubed. And then finally, we multiply the entire thing by r to get our shear rate. And so that is equal to angular velocity times k squared over 1 minus k squared times negative 2 outer radius squared over r squared. And so that is our relationship for our shear rate. So we can evaluate the shear rate at each of the cylinders. So first, we'll evaluate it at the inner radius. So we'll have that the shear rate is equal to omega times k squared, 1 minus k squared times negative 2 outer radius squared over the inner radius squared. And then if we plug in our ratio for k, we'll have that the shear rate is equal to omega times inner radius squared over outer radius squared, 1 minus inner radius squared over outer radius squared times negative 2 outer radius squared over the inner radius squared. And then we have some cancellations. So that cancels with that, that cancels with that, and we're left with shear rate is equal to negative 2 omega times 1 over, and then for this I'm going to find the common denominator like I did before, so that's r squared minus r inner radius squared over the outer radius squared. And so then we can flip that and get that the shear rate is equal to negative 2 angular frequency times radius, outer radius squared over outer radius squared minus the inner radius squared. And then you do the same thing for the outer radius, where we have radius r is equal to the outer radius and so then omega is equal to angular frequency times k squared over 1 minus k squared over -2 outer radius squared over outer radius squared, and then the outer radiuses are going to cancel, and we'll be left with omega is equal to, or the shear rate is equal to -2 times the angular frequency times k squared over 1 minus k squared. And so that is the shear rate at each of the two cylinders. Alright, and I just realized we can simplify this one a little bit farther, so if we ignore that last step that I did, we'll notice that this is just 1 over 1 minus k squared, because we didn't do anything with that denominator. We just turn it into r's, and we can turn it back into k's. So we have that the shear rate is equal to -2 omega over 1 minus k squared. Because this up here, I should not have turned into r's. We need to. So then that all canceled. And then this step was not needed. So we can just keep that as k squares. And it looks a little bit nicer and a little bit more similar to that one. So for this next part, I've written the two shear rate equations that we just came up with up here, and erase the rest so that we have room to work on the next part. So next we're going to want to look at torque, and we're going to want to find the relationship between the torque on our inner cylinder and our outer cylinder. So we know that the inner cylinder has torque because there's some force keeping the cylinder spinning. And then we know there has to be a torque on the outer cylinder in the opposite direction, because something has to be there has to be a force applied to keep that cylinder stationary. So we're going to look at 3 general relationships, and we're going to use it to find the torques of these two cylinders. So the first, we have that the shear stress is the viscosity times the shear rate. We also know that torque is the force times radius, and we know that force is shear rate times area. And so we can combine all 3 of these to get a general relationship for torque. So we start with torque is equal to force times radius, and then we can plug force into there. So we got torque is equal to shear stress times area times radius, and then we plug shear stress in there, and we're going to get that torque is equal to viscosity times shear rate times area times radius. And so that's what we're going to be using to find the torque of the 2 cylinders. So let's start with the inner cylinder. So inner cylinder has R equal to the radius of the inner cylinder. So then we'll have our torque is equal to viscosity times shear rate times area times the inner radius. So then we can start plugging some things. So we can plug in our shear rate that we know, which was -2 times the angular frequency over 1 minus k squared. And then we know the area, so the area is the area of contact between the outside of the cylinder and that fluid that's inside of it. So that's going to be the circumference, which is 2 pi r, times the height of the cylinder. And my drawing is kind of bad, I'm going to fix that and show you that these two heights are the same. The heights of the cylinder are the same. And so we're going to use H to denote that height. Alright, so then times H, and that is the area. So circumference times the height is the area. And then times the radius. Okay. So now we want to do the same thing for our other cylinder, where the radius is equal to the outer radius. And again, we've got that the torque is equal to the viscosity times the shear rate times the area times the inner radius. Again, very similar. We can plug in the viscosity, plug in our shear rate equation, which is -2 omega k squared over 1 minus k squared. And that should be big R, because we're at the outer cylinder, not the inner one. And then the area is going to be the same deal. This is the inner radius. So it's going to be the circumference times the height. So 2 pi times the outer radius times the height, and then times the outer radius. All right. So then we want to see, is this torque equal to this torque? So we'll have mu times, I'm just copying this torque down here. And so then we have Ri times Ri, so that's inner radius squared. And we want to know is that equal to this one. And again, we'll multiply the two radiuses. We got 2 pi outer radius squared times the height. Alright. So then you can cancel some things. So mu cancels, -2 omega cancels, 1 minus k squared cancels, 2 pi cancels, our height cancels, and so we're left with our I squared is equal to k squared times the outer radius squared, and then you can take the square root of both of those, and we've got the inner radius is equal to k times the outer radius, which is the same relationship we have up here. So we plug that in for k, we get that inner radius equal to the inner radius over the outer radius times the outer radius, and therefore the inner radius is equal to the inner radius. And so our two torques, the torque on the inner cylinder and the torque on the outer cylinder, are equivalent.